So as I mentioned in today's webinar, we will speak about sub-hourly meteorological data and how does it affect the PV energy yield estimation. My name is Álvaro Pajares. I'm a product owner at RatedPower. I've been working for the company for the last 4 years. I've been working for the customer success team, also as a software engineer. And now I'm working as a product owner for the generation team. And during this session, we will first introduce a bit the topic of sub-hourly, reviewing the importance of the solar resource when carrying out a simulation. Then we will go through an analysis that we did at RatedPower comparing the energy results of hourly simulations and sub-hourly simulations. From this analysis, in the third section of the presentation, we will see the main differences that we found out in this analysis. We will go deeper and try to find the root cause of the differences in energy production. Then we will wrap up with some conclusions about the topic. And finally, we will have some space for the Q&A session that, as I mentioned, at any moment, if you have any question, please feel free to add it to the questions from the tab. So first of all, to introduce the topic, I would like to list here some factors that affect the energy production of a PV plant. The solar resource will be key, of course, when trying to evaluate a location and to build a PV plant. It will be directly related to the location where we are building the plant, but also will be something that is affected by the meteorological data provider that we are using, the time resolution that we are using, and many other factors. Then the equipment installed and the configuration that we are using will affect also the energy production of the plant, what module, what inverter, how we are connecting this equipment, DC-AC radio, and different design criteria that will affect also the amount of energy that we can get from a PV plant. Then in terms of shades, of course, this affect the energy production. As more shades are present in our design, less energy can be produced by the modules. And it's important to mention here that it's not directly related, the amount of energy that we are losing with the shades that we have in the plant, but the energy loss is even higher due to the electrical shading losses that occur in the plant. Then there are also some other losses that we can group in system losses that could be related to electrical losses, such as the transformer losses, cable losses, and all the losses that may happen in a PV system when going from the generation to the grid. And then some others that could include lead losses, degradation losses, plant availability, grid availability, and some others that will affect the energy production that we can have in a PV plant. So today we are gonna be focusing on the first one, on the solar resource. But why sub-hourly? Well, as we know, in the past, normally the simulations that are carried out to calculate the PV energy yield that we can have from a PV plant, hourly data has been the main data that we have been using to carry out this analysis. But nowadays, as more and more PVs being integrated into the grid, we are getting more restrictive requirements from grid operators, for example. They may ask to have power or voltage fluctuations. To get those, we may need to use sub-hourly meteorological data so that we can know what fluctuations we are going to have for specific intervals, for 1 minute intervals, 15-minute intervals, 10, 5, or whatever. Then also for the battery energy storage systems, we are getting more and more batteries in the industry. And to correctly size these systems, normally we may need to have more granular results, also to calculate better the dispatch strategies, and this may make us to go to sub-hourly meteorological data. Then another reason could be that we want to evaluate better the effect of clouds on the energy production, on the inverter power limit or clipping losses. Here we will see this in more detail in the next sections, but mainly with hourly meteorological data, we may be masking the irradiance fluctuations that occur within 1 hour, and this will affect the inverter power limit losses that we have in the design. Then directly we may think that if we go to sub-hourly, we are evaluating more intervals, and so we are getting more precise and more accurate, closer to reality, we may think. And lastly, also nowadays we have more availability of this sub-hourly data. So as we have this data, we can use it for simulating the PV plant. Okay, so now we will go through the analysis that we did at RatedPower. We wanted to evaluate what were the main differences in terms of energy production when comparing sub-hourly simulations with hourly simulations. And to do so, we evaluated 5 different locations, designs in Costa Rica, Chile, Finland, Washington, and Spain, with different meteorological data, hourly, 15-minute, 5-minute, and 1-minute meteorological data. In terms of design criteria, we wanted to also consider the effect that the DCAC radio may have on the results. So we evaluated 4 different DCAC radios, and then the pitch distance will be adapted to the location and the layout, as it's not something that we wanted to optimize here. Then for the equipment, we selected a monofacial module, a string inverter, and also evaluated both trackers and fixed structures. And finally, we evaluated different configurations with a standard layout, but also with layouts with different rotations, so that we could evaluate that also in this analysis. This means that we carried out 800 simulations in total. And in these 5 locations that I mentioned, where the solar resource, as we can see from these different graphs, are very different. If we go to Costa Rica, we can see how the presence of diffuse irradiance is quite noticeable. So we may think that it's a climate that is more rainy or cloudy. If we go to Chile, the presence of diffuse is quite low and the temperatures are higher. We may think that is an arid climate where the presence of clouds is much lower. And then for Finland, we see that also the presence of diffuse irradiance is noticeable, but also the temperatures are lower, which looks like a more polar climate. And finally, for Washington and Spain, the presence of diffuse irradiance is something to consider, but not that much as in Costa Rica. And both climates look a bit similar. For Washington, we have a bit more of diffuse irradiance, but we can think that we are speaking about temperate climates for both locations. So now we are gonna go through the 5 different locations and see what were the differences that we found out when running all the simulations that I mentioned for each one of these locations in terms of energy production. The first thing that we noticed for Costa Rica was the fact that overall for the energy production, we always got less energy predicted for sub-hourly simulations, getting results up to minus 2.3%. If we see the graph that we have at the right side of the slide, we can see the distribution of the simulations within the different percentages. So here, positive values will mean that we have more energy for sub-hourly simulations. Negative values will mean that we have less energy for sub-hourly simulations. And then in different colors, we have also represented the different time resolutions for sub-hourly meteorological data. From this graph, we can see how all the bars are at the left side of the distribution. So as I mentioned, all the simulations with sub-hourly provided less energy. And also we can see how as we increase the time resolution of the sub-hourly meteorological data, as we go into 1 minute simulations, the differences are even higher. So if we go to 1 minute simulations, we have more differences with hourly simulations. Once we went in more detail towards this energy yield calculation, and we looked individually at each one of the losses that occur during this process of conversion of energy, we observed that there were differences not only at the inverter power limit losses. As I mentioned before, these were expected due to the irradiance fluctuations that may happen within the hour. But also we observed that there were differences for the irradiation that we have at the plane of array for both components, for the beam and the diffuse components. If we go to the beam component, here we observe that we always got higher values of irradiation for sub-hourly simulations, as we can see in the graph, and that these differences were up to plus 0.4% of irradiation, which is something that is not negligible, let's say, and maybe something that we want to consider. For the diffuse irradiation, we observed the opposite. We observed that there were always lower values of irradiation for sub-hourly simulations, and that these differences accounted up to minus 0.8% of irradiation. As I mentioned before, for inverter power limit losses, the results were always lower and higher losses for sub-hourly simulations, with differences up to minus 1.6%. And we can observe from the three graphs how, as we go towards 1 minute simulations, the differences are higher when compared to hourly simulations. If we go to the second scenario, to Chile, we can see now how the distribution of energy yield estimation is more centered. We always get less energy for sub-hourly simulations again, but now the distribution is closer to 0%. If we evaluate the beam and diffuse irradiation, we can see how the differences are not that high, and the values are quite close. But again, for inverter power limit losses, we observe how there are always higher losses for sub-hourly simulations. We can see how the maximum values are lower than in the previous case, which looks maybe related to the diffuse component, the amount of diffuse that we have for Costa Rica, but still always higher losses appear for sub-hourly simulations. If we continue to the third case study, to Finland, again we observed that there was always less energy for sub-hourly simulations, accounting up to minus 0.67% of energy yield. And now we observe a change of tendency in the beam irradiation, where we see that there are lower values of irradiation for sub-hourly simulations, getting values of up to minus 0.6%. And for the diffuse irradiation, we observe higher values of irradiation in general for sub-hourly simulations, and as we go to 1 minute, even higher the differences, but also we see a different tendency for 15-minute simulations. Finally, for the inverter power limit losses, again, we observe the same as before, higher losses for sub-hourly simulations. Continuing with Washington, now we observe that still the differences in terms of energy production are similar. We have less energy produced for sub-hourly simulations, accounting up to minus 1.1%. And now we see a difference in the tendency for the beam irradiation and the diffuse irradiation. Well, for both cases, we have lower values of irradiation for sub-hourly simulations. And last, for the inverter power limit losses, we can see how we have higher losses for sub-hourly simulations again. In the case of Spain, we can see how the distribution is very similar to the one in Washington, which also matches with the fact that the solar resource was quite similar. But again, the energy production is lower for sub-hourly simulations. We have less irradiance for at the plane of array for both components, and the losses that we have for the inverter power limit losses, for the clipping losses, are higher for sub-hourly simulations. Again, we can see how the closer we are to 1 minute simulations, the higher are the differences. If we sum up all of these simulations that we carried out, and add all of them to one graph, we can see first in general for the energy yield estimation, we can see how all the simulations are at the left side of the graph, and how we always got less energy for sub-hourly simulations. Also, as we go to 1 minute simulations, the differences are higher, as we have been mentioning during the 5 case that we evaluated. Then if we differentiate in these simulations the ratio that we were evaluating, we have here the 4 different ratios and the inverter power limit losses that we got. We can see how, as we increase the radio, as we would expect, the differences are higher. So these are directly related. Finally, we have aggregated the 3 losses that we have been mentioning before: the beam irradiation, diffuse irradiation, and inverter power limit losses. For the inverter power limit losses, we can see how all sub-hourly simulations got higher losses than hourly simulations. And for diffuse and beam irradiation, we see how the tendency is not that clear, and we have values which are higher irradiation for sub-hourly or lower irradiation for sub-hourly. We have both tendencies, and it's not clear what's going on there. So summarizing, we observed that there were always higher clipping losses for sub-hourly simulations, seeing up to 1.6% of difference in energy production due to the clipping losses, and that these clipping losses are directly related with the intervals resolution, the DC-AC radio, and the effect of clouds. As we have seen before, for the case of Costa Rica, which will be the case where the presence of clouds is higher, we can see how the differences in inverter power limit losses are higher. And for Chile, for example, where the presence of clouds is lower, the differences are not that high. And finally, also that we observed that there were differences on the radiation available at the plane of array for both components, but it wasn't clear what was happening here and what was the reason behind. So now we will go a bit deeper on these different losses that I mentioned: the irradiation at the plane of array and the inverter power limit losses, and try to find the root cause of these differences that we observed. So first of all, going to the transposition to the plane of array, this is the moment where we are transposing the horizontal irradiance that we have to the plane of array. So horizontal irradiance will come from the meteorological data, and then we will convert it to the plane of array. And to do so, for the beam component, we will use the formula we can see here. So this will be the beam irradiation at the plane of array, beam horizontal irradiance, and this will be the transposition gain or the transposition factor by which we will multiply the horizontal irradiance and get the irradiance at the plane of array. This factor, as we can see, will depend only on the position of the sun and on the orientation of the plane of array, where is the structure looking at. If we represent this factor that we can see here for one specific day, here I represented May 15th for Almeria, Spain, and this was the design carried out with a tracker. We represent this factor with both hourly is in orange, sorry, and sub-hourly with 1 minute time resolution for the blue curve. We can see how the blue curve is smooth. It's at every minute it's calculating what's the position of the sun, what's the position of the tracker, and calculating what's the transposition gain that we can have for that specific instant, and how for hourly we are doing that but for a specific interval. So we are just calculating it at some intervals, then it's constant, then calculate another interval, it's constant, and something like that. So we will be seeing for the hourly simulation like a distribution which is more discrete, looks like a stairs-like distribution, while for sub-hourly simulations it's much smoother. So if we go to a specific hourly intervals of this graph, we will go to these two images that we have at the bottom of the presentation. If we go to 7 a.m., for example, and we see what's happening there for both cases, we will see how for the hourly simulation we were just considering the center of the interval, calculating the position of the sun, calculating what's the orientation of the plane of array, and doing the calculation to get what's the transposition gain. So we will go at 7:30, calculate it, and assume that during the whole hour we have that transposition gain, as we are just considering one specific interval for the hour. However, if we go to sub-hourly, to 1 minute resolution, we will see how we are for every interval calculating what's the transposition gain, and how in this case, for example, the value that we were considering for hourly simulation, which was constant, is not representative of the whole interval, as at some point it seems that it was early in the morning, the tracker was fixed, but at some point the tracking started moving, and so the transposition gain was being reduced from some point. So this is considered with the sub-hourly simulation, as we are evaluating all the intervals of the hour, but not for the hourly simulation. If we go to a different interval, to 1 p.m., where the backtracking is not happening as was happening in the early in the morning, we can see how the value that we are considering for the hourly simulation is closer to the average that we may have from the sub-hourly simulation. It's like in the center, but still we are just considering one value for the whole interval. Then here at the right side, I wanted to represent also the beam irradiance fluctuations within 1 hour. In orange, again, we have the hourly value, which will be the average of the irradiance that we have for the hour. And then in blue, the 1 minute simulation, where we have for each minute what irradiance do we have exactly. Here we can see that the distribution of the irradiance within the hour is not constant or linear or something that looks normal, but has some weird fluctuations during the hour. And for hourly, of course, we are considering a constant value. So here, the differences that we observed in the simulations that we carried out for the transposition to the plane of array came from the fact that the sun position and the irradiance distribution that we are considering for hourly simulations may not be representative of the whole interval that we are evaluating. And so we have these differences in the final result. If we continue with the diffuse component of the irradiance, we can see now here that we use the simplified Perth model to do this calculation, to go from horizontal irradiance to irradiance at the plane of array. And now we have a more complicated formula where this factor does not only depends on the position of the sun and on the orientation of the plane of array, but also depends on some empirical coefficients, which depend also on the value that we have for the diffuse horizontal irradiance. Now we can see how the curves are different than the ones that we got for the beam component, and how now the sub-hourly simulation is not that smooth and has some peaks and downs in the curve. And also, again, the hourly simulation is following the sub-hourly one, but has still some stairs-like distribution. If we go in more detail to the specific intervals, we can see how now the sub-hourly simulation doesn't look like that smooth as for the beam components, but goes up and down, which doesn't look like very normal for both intervals 7 a.m. and 1 p.m. And still how there are irradiance fluctuations for the diffuse component within an hour that may not be correctly considered by the hourly simulation. So here for the diffuse component, we can say that there is higher variability on the transposition ratio for sub-hourly simulations, which is due to the irradiance fluctuations. And again, here the factors that depend on the position of the sun and on the orientation of the plane of array will be better represented by the sub-hourly simulation. The last loss, if we go to the inverter power limit losses, as we know, inverters have a window of operation where if we go above a certain value of power, we are incurring into some losses that are, it's normally related to the DC-AC radio. And here, what's happening is the fact that with hourly simulations, we are taking the average irradiance of the hour, calculating what's the power that we can get from that irradiance. And if it's below the maximum, we are not incurring into a loss. If it's above, we are doing so. However, for sub-hourly simulations, we are doing the same, but we are not averaging the irradiance within the whole hour, but we are going interval by interval and calculating what's the power that we have. Due to this, I have represented here a specific case where the values will be different. If we are estimating the energy production for the hourly simulation, we will be seeing at the orange line, and we will be below the maximum power that the inverter accepts, so we wouldn't have any losses. However, if we go to the sub-hourly simulation, we can see how here we are being clipped. We are reaching the maximum power of the inverter, and we are incurring into some losses. And at other intervals, we are much farther than the maximum. So for this reason, always for sub-hourly simulations, we will get higher losses in terms of inverter clipping, because for sub-hourly, we will be considering the intervals that are above and below this limit. We will be considering the irradiance fluctuations, and with hourly, as we are averaging the irradiance of the hour, we are not considering these fluctuations. So as conclusions from this talk, we can say that hourly meteorological data mask irradiance fluctuations that may happen within 1 hour. This will have implications on the transposition to the plane of array for both components, the beam and the diffuse components, and also on the inverter clipping losses. Then also that the sun position which is used for hourly intervals may not be representative of the whole interval, as we are just considering the center of the intervals. And this has implications on the transposition to the plane of array. Then that we expect to have higher differences between sub-hourly and hourly simulations for cloudy climates, higher interval resolutions, and higher DC-AC radios. Then the fact that the use of sub-hourly meteorological data for the simplified Perez model will result on higher variability on the results, as we just saw with peaks and down peaks. And lastly, that there will be some optimal values for the design parameters, as could be the DC-AC radio, that may differ. The optimal value that we get may differ depending on the meteorological data used. If we are calculating the optimal DC-AC radio with sub-hourly simulations, we may think that we may get a lower value than if we calculate it for an hourly simulation. One last thing also to consider here, for the DC battery energy storage systems, this can be even more critical, as the amount of energy that we have available for these systems will be highly related to the amount of energy that we have at the inverter clipping losses. So these differences may be even more critical, and the use of sub-hourly meteorological data may be giving even higher differences. So that was all from my side. Now we can go to the Q&A session, where I will go to them now. Okay, so we have one question which was related to what does each bar stand for. I think that is related to these graphs here. Okay, so here what we are trying to represent is all the simulations that we have carried out for this specific site location. In the different colors, we have the different intervals resolution. So in blue, the simulations that were carried out with 15-minute meteorological data. In green, the simulations that are from 5-minute meteorological data, and in yellow, the ones from 1-minute meteorological data. And in each one of these spaces, we have the difference in energy production that we observed between hourly and sub-hourly simulations. So in this case, for example, this means that there were 2 simulations that were carried out with 1-minute meteorological data that had differences in energy production between -2 and -3%. And here, for example, it will mean that we have 18 simulations that were carried out with 15-minute meteorological data that had differences between 0% and -0.25. And the same will apply for the rest of the losses. Okay, so going back to the questions, I see there's another question, which is how do sub-hourly simulations work in RatedPower's software? Do you run all the intervals, or do you make any simplification? Okay, so here we at RatedPower don't make any simplification, but we just run all the intervals for all the intervals that we have in the meteorological data. So for 1-minute meteorological data, we will run every minute of every day of the whole year. And yeah, that's it. We will run all the intervals that we have in the meteorological data. We will calculate the sun position and the tracking and the orientation of the plane of array for every interval, and then calculate the whole energy production for all of them. Then there's another question, which is, can sub-hourly yield calculated currently using the PV design software? If so, is there a white paper guides on how this can be done? So yeah, we accept currently sub-hourly meteorological data. So far, what you as a user have to do is upload a meteorological data file. We have some generic files that some generic guidelines that you have to follow to do so. And once uploading this sub-hourly meteorological data, we will run all the intervals through our calculation model and get the results at the interval level that you have considered. There is a blog that we have in our knowledge base that after the meeting we will send you um, all of these resources, but there you will find how to do it. Then we have another question, which is, do you think that if we take sorry, that if we take into account sub-hourly resource data, the optimal design will change, lower the CAC radio? Well, I think that normally it shouldn't change too much, but in some cases it will, I think. For example, here we can see how for Costa Rica there were some simulations where the differences in the inverter power limit loss were around the maximum minus 1.6%. And I'm sure that here, if we are optimizing the DCAC radio, for example, and for one simulation we are accounting for these differences and for the other not, the DCAC radio may be, the optimal DCAC radio may be different for both simulations. So yeah, I will say that in some specific locations and designs, the optimal DCAC radio may be different if we use one data or another. And also for the battery energy storage systems, as I mentioned, this can be even more critical, because here we are accounting for a change maybe from getting a 2% of loss in clipping losses for one meteorological data, from 2% to 3.5% or something, which is maybe double the losses that we have for the inverter power limit losses. And so the sizing of the batteries will depend on this, and this can be even more critical for that systems. I will say that in general, for locations where the presence of clouds is not that high, and this kind of locations, the differences in optimal values as the DCAC ratio shouldn't be that different, but in some specific case, they could be. So we have another question, which is normally the calculation of the number of modules per string is done with data that has hourly resolution. Have you checked if having sub-hourly data affects the calculation of the number of modules in series? Thank you very much. So here there could be differences, but we didn't notice any, and normally it's because the temperature that is considered for the modules per string will be the minimum temperature of the site, and this minimum temperature will be stable in the early in the morning, or like late in the night at 7 a.m. or say 6 a.m. or something like that. And we will then find big differences in temperature there. So we didn't find in the simulations that we carried out, we didn't find any difference on the optimal modules per string. But there could be, but I think that that's more complicated to happen. Hello, where and when can we access the recording? So we will send you after the okay, it was answered, sorry. We will send you after this meeting the recording. And then the PR estimation will be affected. Well, it will, as the difference in the losses will will happen. So the PR will be affected too in these simulations. And I see there's as a last question, which I think I already answered, but well, do you provide sub-hourly meteorological data in the software? So we don't provide directly this data, but we have we allow users to upload sub-hourly meteorological data so that they can estimate sub-hourly simulations with the software. And yeah, I think that we have already answered all the questions that you had. If you have any after the meeting, please feel free to reach us, and we will try to answer them. And yeah, and that was it from my side. Thank you very much for joining. I hope it was useful. And yeah, see you in other webinars or spaces like this one.